Hello and welcome to RF design tutorial. This is part 2 video of pin diode based RF switch design using Keysight ADS. Just to refresh your memory, in this video series we are talking about going through a journey from an ideal circuit design to more of a practical design where your simulation and measurement results are closely correlating, giving you a good design flow for achieving first pass success. And we have taken this RF switch design as one of the case study. Now before we go through this video, I would again like to extend my heartfelt appreciation to Professor Dennis Derrickson of California Polytechnic, San Luis Obispo, California, and his dedicated students who collaborated with me on this case study. In the part 1 video, we went through the RF switch basics and then we went through a step-by-step design process of a RF switch design, reaching to a place where we had fab-ready PCB layout with all the component values for our successful design of an SPDT RF switch. In this video, we will talk about measured results and the simulation versus measurement result comparison. And I will also give you plenty of troubleshooting and practical design tips, and we will talk about some best practices that you can follow for a first pass success of your RF circuit design. So stay tuned till the end of this video. A lot of useful information will be shared. Now here is what we fabricated based on the design I talked about in the part 1 of this video. Here you can see the bare PCB, the assembled PCB for our RF switch, which was done by Cal Poly students in their lab. And on the right hand side is the measured response of our RF switch done using Keysight PNA-X network analyzer. So once you look at these characteristics, prima facie it looks pretty good because we had our pass band or the desired band from 1.7 to 2.3 gigahertz. And here our objective was to achieve better than 10 dB return loss, better than 1.5 dB insertion loss, more than 30 dB of isolation. So we are kind of pretty much there, meeting all the requirements except one. So when we compare simulation versus measurement, on this slide you can see the blue curve, which is measured using PNA-X network analyzer of Keysight, and the red is your RF Pro ADS co-simulation result. So here you can see it's a pretty decent match, but it's not a perfect match. But some of us would be very happy, in fact, even if we see this kind of result, because we are almost there. So if you're happy, you can switch off this video and focus in your work. But if you're not happy and you would like to understand why there are these differences between simulation and measurement result, stay with me till the end of this video and you will get your answer. Now, when you compare these two responses, what comes to your mind? Number one, we can see there is an increased insertion loss which we achieved during measurement. Secondly, the return loss, which is kind of little off between measurement and simulation, and we can see some amount of shift which is happening. So you must wonder, where are these discrepancies coming from and how can you resolve these discrepancies? And when you think about it, think it like 2 points. Number one, what could have gone wrong which is causing such a behavior? Did we miss anything during the design stage there might be some things which we didn't account for? And remember, this is a project done by graduate students, so they are not super duper RF design experts, so they were also learning along with this process. So it's highly likely they didn't know something and they missed some things in the design stage, which is contributing to this incremental difference. But again, make no mistake, this is a super success for any student fabricating first PCB, which is a real RF switch, and getting this kind of close correlation between simulation and measurement. Now, having said that, we still need to investigate and improve upon our design flow, and that's what we are going to do now. So for investigation of this discrepancy, there are 4 key areas you can look at. Number one, assembly technique, how you simulated things in in your design software versus what is done in real life when you are fabricating and assembling the PCB and you're testing that PCB. So there might be some subtle differences there which can cause the difference. Secondly, vendor component model. What kind of model you used in your design process? What models are you using in your actual PCB assembly? They may have slight differences, so resulting in an overall difference which we are seeing between simulation and measurement. Third, remember, every SMT component will have certain level of tolerance. It could be 0.1, 0.25, 1%, 5%, 10%, 20%, etc. And in your simulation, you might be using one single value, but in the real assembly, it's not guaranteed to have same value. The value can change within the tolerance range as specified by the manufacturer. And finally, your PCB fabrication will always have certain process variation, such as etching factor tolerance, dielectric constant tolerance, etc. So all these things can play a certain a role in creating a difference between your simulation world and the real measurement world. So our focus is what's really causing this difference, and once we know that, it will be easier for us to improve our design flow, so that next design, when we do, we take care of all those things and achieve first pass success to avoid any tuning on the test bench with a real PCB. Alright, so for investigation 1, let's take a look at assembly versus layout EM simulation, because both of them are the gospel truths of their own. Right. On the left hand side here, you can see the PCB which was finalized and sent for fabrication. On the right hand side is the assembled PCB. So notice the layout EM simulation was done with 0402 component because they don't have a very wide mounting pad requirements. That means we could minimize the impedance mismatch between the 50 ohm connecting lines between components and the component pad. So tip number 1, try to minimize those kind of impedance mismatches by selecting the right size of the component. Of course, when you select those components, you have power rating to keep in mind and other factors. But whenever given a choice, pick a component which is closely matching or closer to your 50 ohm kind of interconnecting line. So assembly done by students use parallel components because they didn't have the needed capacitor values, and they didn't realize when they were designing this PCB and loaded for fabrication to check the inventory and make sure they have the right component values. Right, this is another education. So many of our experienced designers also do this mistake, so nothing wrong in that. So eventually what they ended up doing is mounting these capacitors in parallel to achieve the eventual value needed. So this assembly technique created two problems between simulation and test results. Number one, in your actual PCB, you have a wider interface of mismatch between sections because you mounted components in parallel. You can notice the 50 ohm line, instead of seeing a nice slim 0402 pad, now it is seeing 2x of that pad width. Now suddenly you will have much more reflection, and we didn't account for that when we were doing our layout design or electromagnetic simulation. Secondly, parallel component characteristics may not be same as a single component, which will again give you the difference in the overall circuit performance when you are testing. So right now it's apple versus orange which we are trying to compare, because left is not equal to right side. Right? So that's what we are going to do. So how can we go about troubleshooting something like this in ADS? Number one, when I received this design, what I did looking at the assembly, I modified the layout footprint value to have much wider width, closely trying to replicate what is happening in the PCB. So here you can see three components in parallel. So I multiplied the pad width by 3, although it's not a real linear relationship, but it's my best approximation to have or to create this kind of mismatch between the 50 ohm line and this wide line. And wherever it was mounted two components in parallel, I increased the pad width by 2, by the factor of 2. right? That's the one change. And with this layout, I went ahead and performed electromagnetic simulation. And then in the generated co-simulation schematic, instead of using a single component to represent a value, I used the same parallel configuration as used in the real PCB. For example, a 3.3 picofarad capacitance, which we originally needed, you can see there are three 1.1 picofarad capacitors connected, and exactly what I did in my schematic. And same way here, I connected two capacitors in parallel with each having 0.9 picofarad to eventually achieve 1.8 picofarad value as needed. With these two simple changes, when we compare the simulation measurement result, now you can see instead of having 0.8 dB loss in my switch is now giving me 1.3 dB loss in simulation, which is closer to 2.2 dB, which is obtained during measurement. So now we are one step closer. So what does it tell you? It tells you that mismatch does play an important role. Secondly, the parallel component mounting may have incremental impact in the overall RF circuit performance. Now with this change, you can also see the return loss is now slightly better matching compared to the previous case where you saw a much bigger offset. On this side, I have provided a zoomed in transmission response, and you can see the differences is pretty consistent throughout our bandwidth, and it's pretty well defined the trajectory of the transmission response. Isolation, we didn't need to worry because measured isolation is already better than simulated. Remember, this blue trace is the measured response, and it is already offering me more isolation than what I have simulated. And being on a pessimistic side is always better, because if I'm meeting my requirements on a pessimistic side, and if your measurement comes out to be more optimistic, you are 100% guaranteed to meet the spec. Actually, you will better with the spec. So in this case, you can see I'm almost achieving better than 40 dB of isolation instead of better than 30 dB, which was predicted during my design stage. So that's not my worry. My primary worry is to get this insertion loss data correct and a better matching return loss. Pretty good, right? Okay, so before I move on, let me take you through the ADS workspace, which you can download from the link provided in the description box of this video from Keysight Knowledge Center. Remember, for Keysight Knowledge Center, you need to create an account and you should be a supported Keysight customer. So here you will see the circuit design. This is essentially what we talked about in part 1 of the video. And also one important thing to note, you give the same layout work to different engineers and they will do the layout differently. Now depending on how you do the layout, your eventual circuit performance can vary. Just to illustrate the point, here you can see you have layout version 1, and if you have some engineer, he might end up doing layout something like this. And here you can see you have this cross connection for the switch. Remember, we have to pass on the cross connection for the bias supply to maintain forward bias and reverse bias. So somebody might end up doing layout design something like this, where you have a long interconnect going between these bias lines to make that, or to create that crossover. So this could have X performance, and suddenly if you give it to somebody else, which is another layout engineer, he might end up doing a layout like this, where your crossover is minimal and also the interconnect is much shorter compared to the earlier case, because he simply put enough mind to rotate this section here so that you can minimize the length of this interconnect or the via transition which is happening here. Again, this will have performance Y. The performance X could be worse than performance Y. This layout might be much better performing because you are controlling the length of these transmission interconnects, which essentially would cause certain amount of parasitics in your actual response at higher frequency. We try to avoid these interconnecting length as much as possible for a better RF performance or a better high frequency performance. Alright, so these are some basic tips pay special attention to how you are doing layout, and by doing one kind of layout, if you're not getting your response, just take a relook at your layout and think, can you improve? Can you reduce the parasitics? Can you further shorten all those interconnects to minimize the parasitics and achieve a better performance? Alright, having said that, let's see. So this was the switch which was fabricated. Here is the layout which was sent out to fabrication. This is a 4-layer OSH-Park process. You could replicate something like this on your side using your own PCB fabricator, giving a certain technology for your work. And this design was simulated in RF Pro, as I talked about in my last video, which is part 1. And finally, this was the co-simulation schematic which we obtained, where we had a layout with 0402 footprint size being EM simulated, and then RF Pro helped us to create this kind of automatic assembly, stitching these LNC components with the PCB. So this is like a virtual PCB assembly simulation. And then we obtained the final values, which were standard, and we went ahead and created a BOM or bill of material for our design. So let's go ahead and simulate this design. This is the final simulation which we obtained, based on which we went ahead and fabricated the PCB. You can see it is meeting all the performance specification we had in mind. And then based on the PCB we fabricated, we assembled here, and those are the snapshots showing you the various stages. So this is layout co-simulation PCB with component identification. Here is your bill of material table for each of those components, and this is the fabricated bare PCB and the assembled PCB. And the next data display page shows you the comparison of measured response versus simulated response for our switch. And this is what I showed you on the PPT slide moments ago, where you can see a big good amount of discrepancy between simulation and measurement result. But again, it's decent, but it could be much better. Alright, so we have reached this stage, and once you download this workspace from Knowledge Center, you can go and take a closer look at each of these designs for your own reference. Now with the things I just talked about, having parallel component assembly, and I did layout modification here in study 2. You have this layout, and let me switch off all the layer except the con layer, and here you can notice this is a standard 0402 component footprint, and I made it wider based on the assembly which was done on a real PCB. So this pad width is almost 3 times what is being used for 0402, and here is the 2 components in parallel, so this width is around 2 times to take care of that. So wherever necessary, like in this case it's a series RF path, there is a series RF path, so I have made all those modifications looking at the picture or the PCB which I had in hand, which was assembled. And this was again co-simulated, and then we went ahead and performed co-simulation. And so this is the EM response block or EM data block with our modified PCB with wider pads. And then here you can notice the components being changed. Instead of a single component, I'm using multiple components in parallel to reflect the real PCB assembly, so that we can compare apple to apple rather than apple to oranges. And as illustrated in the slide, now we see simulated response to be 1.3 dB, which is closer to 2.2 dB compared to the previous response, which was around 0.8 dB. And also the return loss is slightly better matching. It's not very well matching, but much better matching compared to the previous response. And this is a zoomed in transmission response with a line marker for your reference. Looks pretty good so far, right? Okay, so let's move ahead. Let me close some of these windows and let's get back to our slide. So that was investigation 1, which brought us one step closer to reducing the discrepancy. Right. So what are the 2 key takeaways from this investigation? Number 1, Width mismatch on RF PCB causes impedance mismatch, and this could result in introducing the undesired impact on your circuit performance. So pay close attention to the region of impedance mismatch and account for it during your electromagnetic simulation and co-simulation. That's number one. Number two, single SMT may or may not be equal to multiple SMT components connected in parallel in terms of electrical performance. So in your co-simulation schematic, model the eventual mounting methodology so that if there is some undesired impact due to such component mounting, you can take care of it and you can correct for the distortion produced due to such component mounting. Alright, so two key takeaways to take out from investigation number one. Alright, so let's proceed with investigation 2, and here we will talk about vendor component model. Remember, since this design is again done by students who are still learning the art of RF circuit design or a practical circuit design, they didn't include the eventual vendor component in their design. They assume that discrete component which is offered by the design software library was okay. So now we will see if this vendor component model has slightly different characteristics and can it create an impact on RF circuit performance. So in the real PCB, we use Murata components of these series. So I went ahead and downloaded Murata library. So I will provide this link in the description of this video. You can go ahead and download the same at your side. And now I added this library into my ADS workspace. And again, if you are not sure how to add vendor component library, how to work with that, I have a video talking about how to use vendor component library in ADS. Look up on my YouTube channel and the Learn ADS in 5 minutes playlist, and you will get a video talking about all the steps you need. It's a very simple process, but if you haven't done it anytime, refer to that video. Alright, so with this, I don't need it to do the EM simulation again, because eventually nothing on my PCB is changing. It already has a wide mismatch pad condition and so on. I only modified the co-simulation schematic and I replaced the ideal L and C components with the needed Murata capacitor and inductor. So with that change, when I perform the simulation again, now you can see even better matching response. Now our insertion loss, which was 1.3 dB, is now 1.6 dB. That means the actual vendor components are a little more lossy than what we were using in our circuit design. So now eventually from 0.8 dB we increase it to 1.3 dB by modeling the real parallel mounting and wider mismatches pad, and now we increase that further to 1.6 dB by accounting for the real loss of the vendor components. And now with the vendor components, if you look at S11 response, is almost overlapping. You hardly can get much better matching than what you are seeing on the screen. There's almost overlapping response. And the insertion loss is also very, very close, as you also can see from the zoomed in plot. Alright, so investigation 2 also opened up some ideas. So again, before I go further, let me go back to my layout and let's talk about study 3, which is having only this co-simulation schematic which is changed. And in here you can notice the Murata capacitors and Murata inductors being used in design. And I have this design kit which I added in my ADS work, and I use components from that library in my co-sim schematic. The EM simulation is the same as we obtained earlier. So now let's go ahead and simulate this, and now you can see the same response which I just showed you on the PPT, where we have 1.6 dB and the measured is around 2.2 dB with a nice S11 matching. Isolation was never my concern anyways, so this all in all is giving you a pretty good response. Alright, so now let's go back to our slide deck here and proceed. So again, what are your two key takeaways from this investigation? Number one, remember that vendor component model may use either a measured S2P file behind the scene or a verified SPICE model. which may have a unique characteristics compared to a regular discrete component which you use from your software library, even if you include a Q factor specification in those components. So when you are trying to meet a certain stringent specification and you had a lot of either a cost constraint or size constraints or whatever, try to use actual vendor model wherever possible to reflect the near real life situation. And also, as we spoke earlier, when mounted in parallel, these components may have a different performance, especially when you start using actual vendor models which is S2P based, and when you connect 3 S2P or 2 S2P files in parallel, the performance will be different than a regular single S2P file for the eventual value which you are trying to use. So this stays constant, but this increases the accuracy which you can obtain in your circuit simulation. All right, pretty good so far. All right, so hopefully you are getting some real life design tips which you can take care when you do your own circuit designs like that. All right, so out of 4 investigation areas, we already covered 2 and we have achieved very close. Now, what can we do with component tolerance? See, while vendor models gives you higher accuracy, but they have side effect too, because most of the vendor models, not all, but most of them would be an S2P file based model. That means you might see component like capacitor, symbol or inductor, but behind the scene they don't have an actual SPICE model. They will be measured S2P file, which vendor will measure on a test fixture. They will de-embed the test fixture and give you the intrinsic S2P file for that component. But now that becomes a static file. That means you cannot perform statistical analysis to take care of the impact which might be caused due to component tolerance. So I'll give you another tip, although it's not written on this slide. So when you are in this kind of design process where you need more flexible control on your discrete components such as inductor, capacitor, try to use regular discrete models, but make sure you account for Q factor in each of those models, especially if you're dealing with resonant circuits like filters or using those components in the impedance matching application. And that component will allow you to do a lot of these Monte Carlo yield analysis and such. You finalize the design, you fine-tune the design. At the last stage, when you're just about to send this board for fabrication, replace them with vendor component models and see whether you still have the same performance or not. If not, you can slightly fine-tune and then proceed for fabrication. All right, so in our case we cannot perform this study because we already have vendor models included, and that is clearly making impact on the circuit performance. Lastly, process variation analysis. So every PCB you fabricate, no matter which fab house you use, they will have inherent tolerance in terms of etching factor, which means the width of, let's say, 0.1 mm may not be 0.1 mm in the real fabricated PCB. It would be some plus minus variation. And as you know, width is equal to impedance. So if you have width change, you will have slight impedance change. So if you're relying on impedance matching, etc., that might get disturbed a little bit. But if your circuit is very sensitive, only then you will see a huge impact. Otherwise, it will have a marginal impact, but nothing which you really need to worry about. Your dielectric constant of the materials may have certain plus minus tolerance that may also play an important role. And if you remember the transmission line characteristic impedance formula, you have dielectric constant bold and bright in that formula. So any change in dielectric constant will also create a little bit of tolerance into the impedance calculation, which eventually will play a role in the overall response. But this variation, while they may be there in real life, but for our switch, is it valid? Now if you look at our switch design, it is more dominated by L and C, and PCB is only playing a very small part of it. It has part, it is introducing additional loss, but by having little bit of edge factor, little bit of dielectric constant variation, we are not expecting to see a huge change in our circuit performance. It's more of L and C based performance variation. However, if you're designing things which are more dominated by transmission line structure, such as coupled bandpass filters or transmission line oriented impedance matching and so on, then yes, these things can be more important. And if you're doing such designs, these variations can be very easily simulated with RF Pro in areas. You don't need to have a parametric layout or parametric stack up. RF Pro can automatically do all these kind of variations behind the scene. I have a video about that in my YouTube channel. Look for process variation analysis with RF Pro and you will get all the needed details and you will see how easy it is to perform those analyses. So moving on, so we cannot do those two analyses. Then essentially when we try to conclude our investigation, what is still causing the difference between the performance in simulation world and measurement world? We have around 0.5 dB difference in our case. You can see rest everything is matching very well. I found out that the connectors which are used in the actual PCB assembly, actually they are not very high quality connectors. They were purchased from Amazon and these connectors are like 6 GHz frequency range, and I have provided the link in the description box and also on this slide here, so you can go and take a look. When I looked at the Amazon page, I couldn't find any data sheet, any insertion loss specification, because remember, whether you are measuring from transmitter to receiver or transmitter to antenna, from antenna to receiver terminal or antenna to transmitter terminal, you have two connectors in the path. Now, and that loss is not accounted for in our simulation. So looking at the characteristic, looking at the quality of this, I don't expect these connectors to be a super high quality because they are kind of cheap connectors, and also they are going up to 6 GHz. It's pretty safe to assume that each connector would be giving you around 0.15 to 0.2 dB loss at 2 GHz. Right? If you are using like 18 GHz high quality connector, I would say at 2 GHz it will only give you around 0.05 dB or 0.1 dB loss, not more than that. But these connectors are not expected to be such a nice kind of connector. Again, it's my assumption. But if you add the contribution by two SMA connectors, which is close to 0.3, 0.4 dB loss, you add it to 1.6 dB, which we are already getting, we are right there between our measurement and simulation response. So here we can conclude that everything has been accounted for in our design flow, which is making impact in the eventual PCB performance in real world, and we have a pretty good understanding of the design flow and what we need to do in order to produce a first pass success. All right, so with having said that, we still have a job to do. We still have a design specification which we're supposed to meet, which was 1.5 dB insertion loss. So given the limitations we have, for example, we cannot avoid parallel mounting, otherwise we could have reduced the insertion loss because we don't have those component values in our inventory. Of course, I can go and buy one and assemble it, fine. I have to live with that lower quality SMA connectors which I have. So I have all these limitations. So what can I do to meet this specification, or at least get little closer to meeting that specification? Because if your spec is 1.5 dB, if you can go around 1.6, 1.65, it still might be acceptable given the limitation. But 2 dB is a little more. It's like 0.5, 0.6 dB more, which is not expected. Can we do something? So pause this video, think about it. Can you do something within the given limitation? And while you think, let me give you a hint. As we talked about in part 1 of this video, we mentioned the high frequency resistance offered by pin diode is inversely proportional to DC bias current, and it acts as a variable resistor. So by adjusting the bias current, you would be able to control the resistance offered by diode, and then you would be able to control the insertion loss offered by a diode. So think about it. Anyway, for this tutorial's sake, let's keep moving forward. So going back to our design, we are using 560 ohm as our bias resistor because we wanted to keep power dissipation to a minimum in that diode, which was around 11 milliwatt. Changing that bias resistor to around 50 ohm will increase the power dissipation to around 111, but still will be less than 50% of the max specified by the manufacturer. Now what is this 50%? In RF microwave world or electronics world, 50% is kind of considered to be a thumb rule. So whatever is the maximum specified criteria for a particular component, ideally the rule of thumb is you don't cross 50% of that, especially power dissipation, as much as possible. So if this diode is rated for 250 milliwatt, max I can stretch this diode to be is around 125 milliwatt to ensure the longevity of the product I'm designing. It's not that you cannot cross that threshold. You can always operate the diode to 200 milliwatt. That's fine. It's just that diode aging will be much faster compared to if you're making those 50% derating guideline. All right, so but this change, if I reduce the resistor, it will pump up the bias current through the diode. That means it will reduce the resistance offered by diode, eventually affecting our insertion loss. So I went ahead and did a simulation experiment. Because simulation is my virtual world, I can do whatever I want. I replaced 560 by 50 ohm, and now you can see the insertion loss with Murata capacitors mounted in parallel with wide layout co-simulation result. I'm able to achieve around 1.1, 1.2 dB, and if I add 0.3, 0.4 dB of the SMA connector, I will still be meeting my S1, S21 specification or the transmission specification. Return loss was never a problem. Isolation was never a problem. I was already meeting those before. All right. So this gives you hint. Now, how do I prove it in reality? Well, in reality, I didn't want it to remove that component and solder a new component because I don't have 50 ohm in my inventory with me, since I take care of design software most of the time. So I went ahead and increased the bias supply of the diode, which essentially means the same thing. I would like to push more current through the diode to show you a proof of concept. So when I change from 3.3 volt to 10 volt, you can see the insertion loss of the measured PCB of the fabricated PCB reduces from 2.2 dB to around 1.8 dB. So that's 0.4 dB reduction in the insertion loss. So this shows you, given the limitation, you can still make the circuit meet the specification. Although all these things wouldn't have been required if we would have the components in first place and we didn't do that kind of mismatch in the layout. But having said that, you still have a chance to meet the specification as you need, and this demonstrate we can still get the circuit right. So that's all for this tutorial. I hope the content I presented is going to be useful for your design work. And although we have taken RF switch as our case study, but this concept is equally applicable if you are doing oscillator design, mixer design, amplifier design, power amplifier designs, and so on and so forth. All these references I'm again going to put in the description box of this video, which will give you more learning avenues about PN diode, about switch design, and also you can subscribe to my YouTube channel. There are plenty of videos to enhance your knowledge in multiple areas, and also our team manages what we call as a tech tip channel. That link is also provided. You will also get plenty of useful videos contributed by our worldwide application engineers on that channel. So with that, thanks a lot for your attention. I appreciate you staying with me till the end of this video, and wish you all the best in your design work. Take care, my friends, and happy designing.